talk there. So as you see our next speaker, Matt Manor. So I was giving Matt grief a little while ago. I mean, some of you have probably seen it on an aircraft at some point. There's a movie called We Started a Zoo, I think it is. We bought a zoo. And I said to Matt, I think you've actually started like a core scanning company here. But anyway, so Matt was interested from some of the data sets that we had. We had some hyperspectral data sets that we're trying to get some more value out of. And so Matt's been working with Cassidy to develop a workflow for squeezing more value out of those data sets. So Matt's a postdoc who's been doing lots of stuff with MDRU, been with us for about a year, and this is a pretty interesting piece of work. So over to you. Thanks, Matt.
Thanks, Sean. Yeah, so let's open the black box. So we're going to talk about hyperspectral data imaging today. Cass set me up nicely with the amount of mineralogy talk that she was doing. But just to introduce everyone to what a hyperspectral data cube is, these are imaging systems for mineralogy. And at the end of the day, hyperspectral data is one of the few data sets that us as geologists have at our fingertips to identify minerals in near real time. So hyperspectral data cubes, or data scanning or core scanning in general, is a rapid high spatial resolution mineral identification process that we use across the mining value chain. Data cubes are very large. These are, so one of the data sets we've been looking at is about 5,000 meters of drill core that includes the Veneer and Swirr spectrums. This data set is over 1.5 terabytes in data storage. So these data cubes are very difficult to store, they're difficult to process, and of course, difficult to view, which is why service providers kind of have a hold on this at the current time. Many researchers are tackling different aspects of using data cubes, including mineral interpretation and training from SEM and microXRF data. There's been some initiatives to look at how to better store and process this data in near real time. As well, there are a number of open source Python processing tools that have been used even at the commercial scale, like Highlight and HyperPy. So just to kind of set the stage, a data cube is a three-dimensional piece of data. So during our core scanning, we have a spatial coordinate, an XY coordinate, and each coordinate or pixel has one spectrum associated with it. So you'll see in the slides coming up, I'll refer to each typically as a pixel. So we have a coordinate and a wavelength associated with that. So the challenge with working with data cubes is that, well, number one, hyperspectral imaging can be produced by service providers currently across the electromagnetic spectrum. So this includes the visible, shortwave, medium wave, and long wave infrared, most commonly. These can often be merged or co-registered with different types of data analytics, including XRF, DEM, magnetic susceptibility, etc. Libs, that's another one. The service providers generally produce outputs in large batches for drill programs. So this is kind of why there's challenges in dealing with this data, because most companies are dealing with large quantities of data. So challenges around this include the background data, or all the spectra that are populated from this type of analysis, and the QA/QC associated with collecting that data is largely unseen by us as end users. The interpreted products are also limited to either standardized outputs that facilitate each company's business model, or they require additional costs to collect whatever you may need at the end. But at the end of the day, what we're really missing here are products that can be fit for purpose depending on what you're actually doing in your project. So some of the opportunities that we see, hyperspectral data cubes are processed data that come off of an imaging spectrometer, but they're uninterpreted. So the service providers now have interpretation models basically built into these data cube workflows. But we're able to actually acquire the process data and work with that. And greater value can be unlocked by doing this from us as end users, and we can apply these fit for purpose applications. One of the key things that we see moving forward with this is the ability to consistently control the QA/QC of processing and the mineralogy interpretation. So this becomes really important when you're dealing with different data sets at different stages in your exploration or mining or geometallurgy programs. So us at MDRU, our objective is to develop a solution to empower hyperspectral imaging, or HSI, users to interrogate, interpret, and produce outputs that are specific to your changing industry needs and key research goals. So this is an example of a current service provider output. So typically each system will come with a high resolution core photo and a number of different interpreted mineralogy maps, or class maps as they're often called. So in this case, there's illite and muscovite that are filtered products from the 2200. And on the bottom is just a teaser for some of our MDRU workflow processing steps, including a white mica map and a crystallinity map from that white mica composition. So there's a lot on the slide, but this is our general workflow that myself and Cassidy and Sean have been developing over the last year. So the first step is using the spectral geologist, or TSG, which is industry standard at the current time for mineral identification with spectral data. This step includes doing things like mineral interpretation, extracting key wavelength positions from each pixel, looking at spectral geometries of the key features, spectral ratios, like the crystallinity map I just showed, and identifying QA/QC metrics that actually enable us to filter the data more effectively. From this point, we move to open source methods, in particular Python, where we introduce a pixel depth registration. So most data sets come with this, but we are able to do it without depth information, because each core scan has XY coordinates in the direction that it's scanned. So not the end of the world if you don't have that. But and then from there, we do things like removing core tray between core pieces, essentially creating masks, reporting mineral-specific spectral parameters, and ultimately getting rid of all non-rock pixels, so core boxes, tape, etc. From this point, we basically have a product that we can utilize and visualize in many different forms. So we've been doing this with both Python and QGIS because of the spatial ability. So within Python, we can look at things like mineral maps, histograms, downhole trend plots, or strip logs. In QGIS, we can actually look at these core box images and pixels in spatial context, and actually rapidly filter out the data, make calculations depending on different parameters, etc. From there, we get to what the service providers ultimately provide as a downsampled method, which is a much more storage-friendly solution. So we've introduced this through a series of Python codes at 1 meter intervals in some of the data that we're going to show you coming up. But this can also be manually modified to assay intervals or whatever you see fit to your data set. So this general process includes calculating mineral abundances based on the high sampling statistics of the data cubes. So we do pixel counts, which incorporates the basic calculation is the number of mineral pixels divided by the total number of pixels within that scan. When we have these mineral pixel counts, we then report mineral assemblages based on the top 3 counts. Then spectral parameters are averaged across the interval. And we also populate different statistical parameters to be able to address kind of any question you want to pull out of this data set. From there, we do mineral-specific filtering for specific parameters. So an example is that was shown earlier is muscovite or illite filter for the 2200 wavelength. And then importantly, we have built-in internal QA/QC that flags when the requisite spectral features are missing, but the mineral is still reported. So it allows us to go back into the data and kind of deal with that however we would like. So once we have this data that's it's through the open source step and or downsampled, we can use these open source methods to look at the data. So for all the slides moving forward, we have a data set from Northwest Copper that from the Lorraine copper gold silver deposit that Derek presented on earlier. And what I'm going to be looking at specifically is biotite or phlogopite compositions, where one of the diagnostic features of that mineral is the 2380 nanometer wavelength position. So on the bottom left is an example from QGIS, where we have all 2380 nanometer wavelength pixels across this 30 centimeter core length. And the bottom image is the filtered parameter, where we're only reporting mineral ID calls for phlogopite and biotite. When we take this to a whole new scale, the histograms on the right are showing an entire drill hole worth of data. So the top left image contains over 1.6 million pixels in a 230 meter drill hole. And we see a lot of power in this because it not only allows us to look at the entire drill hole, but we're able to actually look at every mineral that's identified in the workflow process and start to identify populations right off the bat before we even downsample. So from this, once we filter to biotite and phlogopite specifically, it drops it to about 436,000 pixels. And within these different groupings, phlogopite is most dominant in this population compared to biotite in the bottom right. But there does appear to be a slight wavelength shift to higher wavelength positions in the biotite by about 2 or 3 nanometers, which could indicate a more iron-rich biotite and a more magnesium-rich phlogopite. When we look at the downsampled data, this is an example from for IOGAS. So we're not only limiting ourselves to the open source software, because let's face it, we're geologists, not everybody knows how to code. It's becoming more common these days, but we need to make this data accessible to everybody, regardless of what software you're using. So this is what the downsampling does, is it enable us to use it in smaller data formats in commercial software. This particular example is using mineral pixel count calculations and statistical analysis over this 1 meter interval that we've picked for this data set. On the left-hand side is all of the data, including aspectral and unclassified mixtures, or mineral identification calls. So the gray shades are what those are. And as you can see, there's still some variation, and you can kind of pick some of the minerals that are present within this drill hole. But the beauty with this data set is we have the ability to filter out these two classes that don't really tell us very much in this scenario anyway. They can be useful in certain situations, but when we filter that out, you get the panel on the right that really allows you to pinpoint domains in this data set a lot easier. And in particular, we can look at specific intervals that have higher abundance of phlogopite, which coincidentally overlaps with the interval that was logged as a biotite altered cyanide. So we have some validation that this works. What this ultimately does is allow for a more robust mineralogical domaining and assessment. And then we can start to look at rock type versus alteration patterns in these mineralizing systems. Taking this another step further, with leveraging statistics, We can enhance the knowledge of our system by not only using just the mean or the median, but also applying things like minimum, maximum, variance, mode, count, etc. So when we pair all this, we're able to look at the differences between these statistical parameters and actually get more value out of our data sets. In this particular example, it's the same hole sorry, not the same hole, different hole that was from the same zone at Lorraine. But I wanted to point your attention to this area where we have high copper, gold, silver grades at the bottom of the hole. You don't really see much in way of variation in the mean, but when you look at the variance in the unfiltered value, there's actually a change as you come in and out of that high grade zone. And when you filter this data, you start to see the same variations in the variance, although a little bit more subtle. But you also see a kick in the minimum values, which shows that there's a shift to higher wavelength positions in this copper-rich domain. So when we take this into Leapfrog, these mineral pixel counts are able to provide us a lot of useful information, including the mineral assemblage and the top mineral that's been identified within your data set. So in this case, this is an interesting one that highlights the dominance of white mica and epidote within this section. So white mica being the orange and epidote being kind of light green. And in this case, highlighted white mica that correlates with some higher grade copper zones. And interestingly, this we think, at least at first glance, this is rock type dependent, because these almost exclusively occur in syenites, where white mica alters the feldspars. We look at biotite absorption, or the 2380 absorption features for biotite and phalogopite combined. These show very subtle changes in the mean values relative to the copper zones. But an interesting thing is when we start looking at things like minimum values, we're actually seeing discrete domains that overlap with the copper zones. So this is indicating higher wavelength 2380 absorption features, or more iron-rich compositions around these copper-rich domains. So now they've shown you kind of all our cool tricks. This is where we're going. So we want to be able to make this workflow fully open source. At the current time, TSG is kind of a rate limiting step because you have to pay for it, and it's quite clunky with data cubes. But it is possible. So some of the things that we're looking at are getting away from typical clustering and grouping algorithms like self-organizing maps and PCA that weight every part of the spectrum equally, but this isn't true with hyperspectral data. So we've done some testing with the spectral angle mapper that Cass mentioned a bit earlier, and this has shown some promising results. We're also looking at identifying more robust workflows for global spectral interpretation using human-driven decision trees to identify the minerals represented in each spectrum. So this would include stuff like the cosine similarity and linear programming that Cass had mentioned in her talk. So, and just kind of a something to leave you with, this is an output from a core photo and the service provider output. We're gathering a lot more information from our process that we can then use in our research questions to gain fit for purpose knowledge for a number of different problems across the mining value chain. And while the TSG process works, and it seems to work very well, we think we can improve upon this even more with these human-driven decision trees, especially with the promising results we're seeing in the spectral angle mapper on the bottom. So with that, I'll leave you there. So stay tuned. There's a lot going on in this space, and very excited to be working with a number of experts in the space to get this developed. So thank you.